Hello everyone, it's Mahin. So in this video, I'll talk about prime numbers and some of its fascinating properties. So maybe some of you know what is prime number, maybe some of you don't. So let me explain a little bit what prime number is. So let's say prime numbers are the kind of integers. Prime number, let's say if we have prime number p, these are the kind of integer that is only divisible by 1 and itself. So let's say we have a random integer a. It's possible, any random integer is divisible by 1 and that's the number itself, right? But prime number are special in a sense that it is only divisible by 1 and itself. It is not divisible by any other number. So what are some of the examples of prime number? For example, let's say 2, for example, is a prime number because 2 is divisible by only 1 and itself. 3 is a prime number. 5 is a prime number. 7, so on. This is a prime number because they are divisible by only 1 and the number itself. And what is an example of something that is not prime? It's a 12, for example. This is not a prime number. So the numbers that are not prime number, these are called composite numbers. So 12 is actually a composite number. And because 12 is divisible by not only 1 in itself, it's obviously 12 is divisible by 1 and 12 is also divisible by itself, but it is also divisible by 2, for example, is divisible by 2, it is divisible by 3, divisible by 4, 6, So that's why 12 is not a prime, it's a composite number, right? So maybe some of you are wondering, what is this table right over here? Actually, I drew this table to explain an algorithm. This is called Eratosthenes' sieve. It was named after Greek mathematician and geographer Eratosthenes. So he created this fascinating technique, fascinating algorithm about counting a prime up to a certain limit. So let's say if someone gives you a particular, someone gives a task of finding all the primes up to a certain number, you can use Eratosthenes' sieve to find all the primes. So let me explain how it works. Let's say I drew all the, I wrote down all the integers up to 100. So if someone asks me, okay, find out all the prime numbers up to 100. What are the process? So it works like that. So what I'm going to do is that I'm going to mark all the multiples of the certain prime numbers. I'll start with 2 and I will mark all the multiples of 2. Why? Because they're composite numbers. So basically I'm marking out the composite numbers out of the table. So I'll start with 2 and all the multiples of 2 are composite number because they're divisible by 2. So they're composite, right? So I'm going to mark all the, multiples of 2 and then I'm going to go back and I'm going to do it for 3. And I'm going to also mark all the multiples of 3 out. And then I'm going to do it with 5, next prime number. Now you can maybe some of you are wondering like how long I have to go because there are so many numbers, 100. Do I have to go really far? Not really. So if you want to check how many prime numbers are there up to 100, you don't have to mark the multiples of all the numbers up to 100, all the prime numbers up to 100. You have to only do it all the prime numbers up to 10. You have to mark the multiples of all the prime numbers up to 10. So basically the general idea is that if you have to check how many primes are there, if you up to k, for example, k is an integer, you have to find how many primes are there up to k. You don't have to mark all the you don't have to mark the multiples of all the prime numbers. You have to do until root over k. That's enough to do it. So in our case, as we have 100 number, in our case we have to mark the multiples of prime up to root over 100 or 10. So basically that means we have to only mark the multiples of 2, 3, 5 and 7. Now the very natural question is why? Why this is the case? Why I have to only check up to root over k, root over 100 in this case? Well, I will leave it as an exercise for you. Try to think about it, why this is the case. It's not a very difficult exercise. Try to figure it out, why this is the case, okay? So in our case, we'll only check until 7. So let me do it right over here. I'm going to mark all the multiples of 2, okay? So basically, I'm not going to mark 2 because 2 is a prime, but I'm going to start with 4. So I've done marking all the multiples of 2. Now I'm going to do the same thing for 3. I'm going to mark all the multiples of 3. 3. Now in case of, let's say, the second multiple of 3 is like 6, which is already marked. So I'm not going to mark that. I'm going to only mark the number that are only mark the multiples of 3 that are unmarked right now. So I'm going to do that with 9, for example, is 1. Alright, so I'm done marking all the multiples of 3. I'm going to do the same thing for prime number 5. Alright, so I'm done. And finally, I'm going to do this for the same thing for 7. That's it. So we're done basically. So the remaining number that we have here that we did not mark are actually prime number, right? So if you count carefully how many prime numbers that you have that are all the unmarked number basically are prime. If you count them, you'll see there are exactly 25 prime numbers up to 100. So there are 25 prime numbers smaller than 100, right? Right. Now you can ask the same question. Okay, what about how many prime numbers are there up to 10? If we count, there is 2, 3, 5, and 7. Only 4, right? There are four prime numbers up to 10. If we take the percentage here, the density of prime number, right? Up to 10, how many percentage of numbers, how many percentage of integers are actually prime? So up to 10, there are 4 prime numbers. That means the percentage of prime that we have up to 10 is 40%, right? So up to 10, I'm gonna write it right over here. So up to 10, let's say we have the density of prime number is 40%. Up to 100, we have 25 prime. That means the density of prime is 25%, right? Now, if you draw this Eratosthenes for 1000, 1000 integer and try to find how many prime numbers are there up to 1000, that will be very big, like a very, very big sieve, and it will take a longer time. I'm not going to do that here. But if you want to do it, you can try to do it, and you will see that there are 168 primes actually up to 168 primes up to 1000. So if you take the percentage, it's actually 16.8, the density of prime. So maybe some of you are noticing a pattern. The density of prime number is slowly decreasing. The further we are going, the density of prime, how dense prime numbers are, it's actually decreasing, right? So the larger number we search into, the frequency of prime we will get it's gonna get lower. So a very natural question will be, well, is it possible that after a while the density of getting prime will be so low that after a while maybe there are no more prime numbers? Maybe after a while all the numbers are composite number, right? Or in different words, is it possible that there is a largest prime number and after that there are no other prime number? Which is a very fascinating question, right? Luckily for us, in ancient Greece, one of the greatest thinker of all time, Euclid, thought about this question and actually found the answer. He found that there is no such largest prime. He found that there are infinitely many prime numbers. And the way Euclid proved that there are infinitely prime numbers is at the same time so profound, but at the same time very simple. The proof is very simple. You don't need to know any advanced mathematics to know the proof. It's very simple, but at the same time very fascinating. So in this video, I'll try to show how Euclid proved from, like, let's say 2400 years from now, how Euclid proved that there are infinitely many prime numbers. Okay, so I'll try to show it in this video. So before we show how Euclid proved that there are infinitely many prime numbers, we have to first talk about something else. The method that Euclid used to prove that there are infinitely many prime numbers is called proof by contradiction. Proof by contradiction, or there is another name which is called indirect proof. So most of the mathematical proof that we see are actually called, we use the method called direct proof. But sometimes the direct proof it's not very effective, so you have to use proof by contradiction. So what Euclid did, the heart of Euclid's argument is that he said that, okay, let's say there are not infinitely many prime numbers, there are finite number of prime numbers. If there are finite number of prime numbers, what does it mean? Well, it means there has to be a largest prime. If there are finite number of prime numbers, there has to be a largest prime, right? And he said that let's assume the largest prime is PL. Right? As simple as that. So that means this is the largest prime. After that, all the numbers that we have are composite number. Okay. So we can just write all the prime numbers that we have in a set. So what are the set of all the prime numbers? It will start from 2. 2 is the first prime number, right? And then 3, and then let's say pk. Pk is, let's say, the kth prime number. Kth prime number is pk. Pk is basically the notation for any arbitrary prime number. Okay, it's a kth prime number. And then the largest prime is pl. So these are the sets of all the prime out there. Okay. Now, what Euclid did, that was something also quite genius. He said that, okay, let's form a new number. Let's construct a new number which will be the multiplication of all the prime plus 1. So he said that let's create a new number. Let's say m. M is a new number. What is this number? M is the multiplication of all the prime plus 1. So we're going to multiply, or it's a product of all the primes, multiplied by pk, multiplied dot up to pl, which is the largest prime, plus 1. He added 1 with it. Now this number m, this is way larger than pl, right? Because we multiplied all the other primes with pl. On top of that, we added 1 to get m. So m is obviously way larger. Also, this is how we show it's way larger. In mathematics, this is the notation. Then pl, right? Well, what does it mean? It means m is a composite number because we already assumed that pl is the largest prime. That means any number larger than pl is composite. That means m is composite number, right? If m is composite, well, what are the definition of composite number? I already told it earlier. I already explained earlier. The definition of composite number are the kind of composite numbers are the kind of number that is divisible by at least one prime other than 1 and itself. So m has to be divisible by at least one prime other than m itself and other than 1. That means m is divisible by one of these primes because these are all the primes that we have. This is the list of all the primes that we have. So m has to be at least divisible by at least one of these prime, right? Because m is a composite number, so it has to be divisible by at least one of the prime from here. So let's say m is divisible by one arbitrary prime number pk. So that means we can write m as like this. M is equal to pk multiplied by some integer. Let's say that integer is something like c. Right? It's an arbitrary integer. So we can write m equal to pk multiplied by c, right? So if we do that, what I'm going to do is that I'm going to replace m with pk multiplied by c. M equal to pk multiplied by c, where pk is one of the arbitrary prime and c is an integer, an arbitrary integer. And on the right side we have this 2 multiplied by 3 multiplied by, let's say, some prime, and then pk multiplied by pl, which is the largest prime or the assumed largest prime, plus 1. Now what we are going to do is that we are going to divide both sides of the equation by pk, right? If we do this, if we divide both sides of the equation by pk, on the left side we will have only c, because on the numerator we have pk, and if we divide it by pk, they will be cancelled out. Those two pk's will be cancelled out. On the left side we will only have c, which is an integer. On the right side, what we will have? Well, we have pk PL over PK plus 1 over PK, right? Now, this expression right over here, this side, this part, right, of this whole right hand side, this is actually an integer because PK, this PK right over here is one of the prime here. That means PK will divide itself, of course. That means PK will divide this whole expression. That means this part will be integer, right? Let's say this is an integer. We can denote it as M. So C equal to M plus we'll have here 1 over PK. This is clearly not an integer. So if it is not an integer, this whole right hand side is also not an integer, right? If right hand side is not an integer, but left hand side, this is an integer, right? C is an integer. So we got an equation finally where the left hand side is an integer, but right hand side is not an integer, which cannot be true, right? I mean, if they're equal, both sides of the equation has to be integer. But what we are saying is that the left side of the equation is an integer, but the right side is not an integer, which is a contradiction. The contradiction we are looking for. That means the only resolution here is that the reason of this contradiction is that our initial assumption that PL is the largest prime was actually false. Our initial assumption that there are finite number of prime numbers and that PL is the largest of all those primes are actually wrong. There are no such PL exist. PL doesn't exist. There are no such largest prime number. That means there are infinitely many prime numbers. This is how Euclid proved it. Fascinating, isn't it?